So, what is going on, Gremlins? It is Monday the 8th. I just watched the eclipse and my eyes hurt. So, today we are talking about balanced trees. So, if you'll remember a couple weeks ago when we were covering balanced search trees, that's not what I want. We ran into this problem in which we had a binary search tree, but it wasn't balanced. So, with our left tree, So with our left tree, if we want to find the number 6 in our tree, we're going to have to check 6 nodes. So 1, 2, 3, 4, 5, and 6. With this non-balance, turns our performance from, a big O of log 2 of n to just big O of n. This is a massive performance hit. So compared to the tree on the right, if we want to find the number 6, we have to check 1, 2, 3 nodes. So if we can help it, we want our trees to be balanced, and we're going to cover that today. So we're going to talk about, or at least start talking about, AVL trees. So what does AVL stand for? I'm going to butcher this name. I'm a white person and I hate it, but it is a Adelson, Velsky, and Landis tree. It's named after the inventors. Actually went and dug up the paper they wrote on it. This was back when education was fantastic. So it was written in 62, 61, 63, somewhere in there, so like 61 through 63. It is 5 pages long, and it's understandable. I was able to sit down and read through some of it, and I'm like, hey, I know what they're talking about. So if you're a big nerd and you want to go read what they cooked up in the 60s about trees, be my guest. The link is at the bottom. But what is an AVL tree? So 2 different things that we have to talk about. A AVL tree is a version of a binary search tree. So everything that we've learned about binary search trees apply here. It's a balanced tree, is a self-balancing tree at that. So this means that the height of the left subtree and the height of the right subtree differ by at most 1. So instead of having this monstrosity of basically a linked list, all of our trees will end up looking something like this in some way, shape, or form. That looks horrible. My bad. So, I always try to throw this slide in, like, why are we learning this? Why are we using it? Since it's just a different way of a binary search tree, or a different version of it, different implementation, anywhere that you can use a binary tree, you can use an AVL tree or a red-black tree. So, binary search trees, heaps, we're going to be talking about that in a few weeks. Huffman coding, syntax trees. There's a couple others, I have no clue what they are. Hash trees. I stole this from Geeks for Geeks, but it's kind of a breakdown between the 2 trees. If you want the TLDR of this, an AVL tree is more complex, but performs better. So, looking at the left side, in a standard binary search tree, we do not follow the balance factor. It's simple to implement. The height or depth is, or can be, big O of n in worst case compared to big O log of n. Searching sucks in case it's imbalanced versus searching is efficient. And then this line right here with our AVL tree structure. So if you'll remember, I need a white space right here in the middle. We'll have some sort of struct node with left subtree, right the data, and then some sort of balancing factor. So we get a new node or a new sort of struct member we have to worry about, but in the end it does help quite a lot. On the other two, not a balanced tree is a balanced tree, and then easy and complex. So how do we tell if a tree is balanced, at least with AVLs? We have to calculate the balance factor. So all the balance factor is the height of the left subtree and the height of the right subtree. If you'll remember, the height is just how deep a tree goes. So if we start here, let's say this is our root, we have a height of 3. Maybe it's 2, but either way, we have some sort of height that we have to worry about. If we have a tree that looks like this, I put 3 arrows in a row, love it. If we have a tree that looks like this, we take a look at the height of the left subtree from our root. Is it 0, 1, 2? We're saying 0, 1, 2. That sounds safer. But we have a height of 2 on our left subtree. If we look on our right, we have a height of 2. And so if we do 2 minus 2, we have a balance factor of 0 at our root node. For a tree to be considered balanced, we need a -1, a 0, or a 1. The negative numbers come from this right side. So if we had 1 less, so 1, we would have 2 minus 1 and have a balancing factor of 1 at this tree. So if your right side is deeper than your left, your number will be negative. So we've got this tree here. I threw it into OneNote for you, and we can go through and calculate the balancing factor for each node. So starting down here at 1 and 10, or I guess our leaf nodes, they do not have children, so we have no subtree to worry about. So these balancing factors are going to be 0 across all of these leaf nodes. If we look at the 6th node, we have 1 child on the left and 1 child on the right. So we're going to have 1 minus 1, which is 0. For 48, same song, same dance, 1 minus 1, 0 as our balancing factor. Did this tab out correctly? It did, cool. And then whenever we get to 19, this is when we start cooking. So looking at these two subtrees, on the left side, we have 2. So it's going to be 2 minus, and then we have 1 depth here, because we only go down 1 step, 1. So at 19, we have a balancing factor of 1, which means we are slightly left-leaning. Then up here at 25, we have a depth of 1, 2, 3, minus 1, and 2. So come back up here, we have 3 minus 2, so our balancing factor at our root would be 25. To double check this with a PowerPoint, at 1 we're going to have 0, 6 is 0, 10 is 0, 19 is 1, 0, 1, 0, 0, 0. So, thumbs up. If we look at this one, if we insert a node 12 right here off of the right child of 10, we get unbalanced. So if we go through and calculate again, 12 is going to have 0, it has no children. 10 is going to have -1, and we get that from 0 minus 1, no child minus 1 child. If we look at 6, we have 1. I'm struggling with numbers. Not my day today, apparently. We have 1 minus 2, which is going to give us a -1. If we look at 19, we're going to have 1, 2, 3 minus 1. So, or 1 minus 3. So we get no, other way around. I'm lying through my teeth. 3 minus 1, we get a 2 on our balancing factor. So this screams bad. This screams we are unbalanced and we need to fix this. So looking through at 19, we have a balancing factor of 2. At 25, a balancing factor of 2. If we do 1, 2, let me clean this up a little bit. It's my bad. So we are going to be subtracting 2 from whatever our left side is, and we go 1, 2, 3, and 4. So 4 minus 2, we get a balancing factor of 2. So something has to change. How can we make a tree unbalanced? So 4 different ways. We can insert into the left subtree of the left child, the right subtree of the right child, the left subtree of the right child, and the right subtree of the left child. If we're inserting, chances are we are making it unbalanced. This is a better thing to remember than all 4 of these. So, how do we fix it? I lied. It's not the next slide. We just kind of reiterate that an AVL is a binary search tree, a balanced binary search tree. So, looking at these 2 trees, I can name them if you want. This is going to be tree A and tree B. Is it an AVL or not? So with AVLs, there are 2 things that have to happen for it to be an AVL. One is that it has to be a binary search tree, and number 2 is the fact that it has to be balanced. So if we go and calculate our balance factors for our left tree, we get a 0, a 0, -1, a +1. Here we would get a 0 because we get 2 minus 2. This one is going to be 0. And if we look at node 10, we get 3 minus 1, which would be 2. So this tree is unbalanced, meaning it is not an AVL. No AVL. Looking at tree B, just looking at it, we can tell, hey, this is balanced. Unfortunately, it is not a binary search tree, and this is our culprit. So if we look to the right side of 5, we notice that its next child is 1. 5 is greater than 1. I should say 1 is less than 5. Looks better. 1 is less than 5, meaning that it should be on the left side of 5. Same thing, 12 is greater than 5, but it is on the left side. So this is not an AVL, because it doesn't cohere to the BST rules. This is the slide I was looking for. So how do we fix this unbalance? We have 4 different ways we can do it. We can rotate left, we can rotate right. These are single rotations, we only do 1. Or we can slam them together and do a left-right rotation or a right-left rotation. Right-left rotations are a little more complex since we're doing 2 of them, but we're going to walk through them in the next couple of minutes. So, given this tree, we need to find where it needs to be rotated at and do the rotation. So to do that, let's calculate our balance factor. So 0, we're going to get a 1 here, 0, 1, 0, and then we do a 1, 2, and 3 minus 1. So 3 minus 1 is equal to 2. This tree is unbalanced. So we need to do a right rotation on our root node, this 12. So we are going to the right. We want to take everything and shift it this way. So one thing to keep in mind is, since we are making 10 our new root node, we're going to have 12 go here, 15 would go next. If we look, 10 has a right child of 11. If we keep it in this left subtree, I'm going to try to draw this graph in half, or this tree in half. if we keep it in this left subtree, we are going to mess up our binary search tree. It should not be there if 10 is our new root. So what we have to do is to shift it to the right side and put it as the left child of 12. And everything else comes up, so 9 and then 8. And this is what our right rotated tree would look like. If we want to do a left rotation, let's go through and calculate. So 0, -1, 0, -1, 0, 1, 2, 3. This is going to be a -2. We get this by doing 1 minus 3. And so we need to do a left rotation on 9. So we're going to take everything, shift it to the left. So if 11 is our new root node, we get the same issue. We can't have 10 be in the right subtree of our graph, or of our tree. So we move 9 over here, and we move 10 to the right side of 9. 8, we throw a 12 here, and then a 13 here. My drawing sucks, but this is balanced. So we have this height completely filled up, and everything here is on the same level. So that is how a left rotation works. And now we start cooking. We get funky with it. So this is going to be our left-right rotation. So let's go ahead and calculate this. 0, 1, 0. This is going to have a 1, because 1, 1, 1. Because 2 minus 1 would be a -1. Up here would be a 2. Yeah, and then 0. So you may be asking yourself, oh, why don't we just do a right rotation on this? Since we have more children here, we can't really do that. We'd have to move too many nodes to the other side of the graph. So what we're going to do instead is to do a left rotation here, and then do a right rotation on what's left there. So for the first rotation, 12 is going to stay where it's at, 15 is going to stay where it's at, but we're going to rotate the left side of our graph. So we move 10 up, 8 down. So we're going to put 10 here in the second position. 8 is going to be on the left, 6 is down here, then the right child is not going to be 9 because that would mess up our graph. It's going on the right side of 8. Let me double check that off of the old stuff. So yes, we would put 9 here. Sorry about that. Recalculate all of our factors. So 0, 0, 0. We get a 2 minus 0, so we have a 2 here, 3 minus 1, and a 2 here. Now we need to do a right rotation based on 10. So we're going to move everything to the right. So we're going to do 10 is the new root, 12 is the right child, 15 is the right child of 12, and then we get 8, 6, and 9. So one thing that you always have to keep in mind is that the binary search tree property is consistent. We had to move 9 here because if we had it, let me rephrase that. Since it was on the left side of 10 in our original graph, and we were moving 10 up here where 8 is, we can't keep that connection. We have to move it somewhere. So we move it to the right side of 8, and we call it a diddly done day. Finally, we have a right-left rotation, in which we are going to rotate right and then to the left. So let's go ahead and get these numbers cooking. We have a 0, a 1, a 0. This is going to have a 1 on it. This is, 1, 2, 3 minus 1 minus 3. We get a -2, and we know we need to rotate. So we're going to do a right rotation based on 10. So we do a right rotation. I should say based on 12, that's my bad. So we do a right rotation, move 11, and then we do a left rotation. So 8, 6, we're going to have a 10 here. To the right of 10, we're going to have 12. To the right of 15, or to the right of 12, we have 15. And to the left of 12, we are going to have 11. So we have this giant graph. Now we do a left rotation based on 10. So we get 10, 8, 6, 12, 11, and 15. One thing I would like to point out with these double rotations, it more or less has these offset numbers. So we have a 10 and a 9 here, and a 10 and 11 here. If you want to sit and think about it, if they weren't there, it would make the rotation simpler. So, well, I guess we would still be doing a right-left. So let's say 11 was on this side instead. We would rotate 10 up. 11 would stay on this side. We would have a 12, a 15. We need to rotate again. Right? Because if we move 10 up, if we move 10 up, then 11 would attach to 12. I don't know why I went down this rabbit hole. But one thing to keep in mind is you want to start rotations from your deepest depth. So in this tree, we have two unbalanced pieces, our 63 node and our 84 node. We want to start with the 63. We want to balance this out first, because if we didn't, our tree would look like 63, 84, 112, 15, and 12. While this is, it's still technically balanced. The issue stems from it is closer to a linked list than a tree, since all of these are in a straight line. This ruins the efficiency of our binary search tree. So you want to start... I'm struggling today. You want to start from the deepest position that you can. So we get a tree that looks like this instead. It may be hard to see it with a smaller tree, but if our tree was a whole bunch of nodes, this would improve the performance. So there's an in-class practice for it. You can pause if you want. Now we get to sort of dive into the AVL tree code. There's two versions of it. One has a recursive algorithm, one doesn't. I'll show you both pieces. I kind of like you all. So let me go ahead and get this cracked open. For our driver, we make a new tree node named root. We insert, display, print it in order, pre-order, and post-order. So driver is nice and simple. Looking at our tree node class, it's got everything you'd expect it to have. We have a tree node for the left and right side. and some sort of value. Looking through, this is everything you'd expect for a tree node class. Constructor, destructor, get value, get left, get right, set value, set left, set right. So we're more or less just looking at AVL tree.h. And this is, I don't want to say a monster of a file, but there's a lot of cool, like, small working pieces that we get to look through. So within our AVL tree, we have one private function, which is destroy all nodes, and this is a recursive function. So we say, while there are still nodes to delete in the subtree, if node pointers left is not equal to null, we call destroy all nodes on that, passing in node pointer get left. If the right side exists, we pass in destroy all nodes, node pointer get right, and then whenever we bottom out or we don't have anything else to pass to, we delete the node pointer. Looking through our other functions, we have a constructor, a destructor, which just calls. We have a get height, I guess it's just called height, and a diff function. Height is going to find the height of a node and return it, and diff is going to calculate, is the left side greater than the right? Is the right side greater than the left? We have our 4 rotations, a right rotation, a left rotation, left-right rotation, right-left rotation, a function to balance, function to insert, and our displays. So first things first is to find the height of our tree. This is a recursive function. The difference between these two files is an insert. But the recursive version, it's going to say, have I hit a null leaf yet? So if temp is not equal to null, we are going to call height on the left subtree and the right subtree of our BST, our AVL. We're going to take the max between the two, and then we are going to set h equal to max height plus 1. At the end, we return h. I need a tree that doesn't look so scary. So I'm leaving numbers off of this for now, just so I can show how height is going to work. So we're going to call height on our root node. So height of root, it's going to say if it's not null, and then we do our recursive calls. So left height, L height is equal to height of left. So this is going to call the function for the left side of this tree. So it's going to go here. We do the same thing. We check the left side. I'll actually add one more node here. So we need another left height is equal to height. I'm shortening this. We go here. Left height is equal to HE of L. One more time. And then we hit rock bottom. Is equal to... I'm writing stuff down at this point. I do not register what's going on. So whenever we hit this bottom node, I'm going to write bottom here. We call left and right height once again. If we look here, it is null and null. So whenever temp is not equal, if temp is equal to null, we skip all that and we return h. So way down here at the bottom, whenever we hit this one, we are going to return h, which is 0 in this instance. because line 72, h is equal to 0. So now that we are starting to come back up from the bottom, we're going to come here. We're going to say, okay, left tree is 0, right tree is 0. We get the max of 0 and 0, which is 0. And then we add 1 to the max. So we return 1. So back up here at this node, keep flipping my pen, that's my bad. We get left height is equal to 1, right height is equal to 0, because this side is null. We get the max between the two, so max between 0 and 1. And then we return max plus 1. Goodbye, node. So here we're going to have a height of 1. Here's going to be a height of 2. Knock another one of these off. Then here, it's going to be 0 and 1, or 2 and 1. We take the max of 2 and 1, return 3. Here we're going to have 3. And so whenever we go through, do it for the right side, we get 1, 1, 2. We take the max of both sides that we were given, so max of 3 and 2, and we return a final height of 4. So that's how the height function works. It's a little bit of a monstrosity, but we take it. If we want to find the differential of the height difference in our tree, we say left height is equal to height of the left side, which will go through that giant recursion that we just did. Right height is equal to height called on the right node. And then we calculate our balance factor by doing left height minus right height. I guess since the camera is flipped, it would be left height minus right height. Say that 5 times fast. So these two functions, it is how we calculate our balancing factor. If we want to do a left rotation on our tree, we're going to make a tree node pointer. So we say tree node, I'm just going to write PTR. We set our pointer equal to parents right. So PTR is equal to parents right. I should draw a graph for this, shouldn't I? So this is right, left rotation. And we are passed in a parent. So we're saying, hey, we want to do a right rotation here. This is going to be our parent. So we set pointer equal to parents right. So right here is going to be our pointer. Then we say parents set right is equal to temp left. Okay, we're scooting it up one. I messed up. This is going to be our parent. This is going to be our pointer. And we say parents set right. So we are setting our right side to temps left. So parents right side is equal to temps left. So we change this one arrow that we have already. And we say, hey, you point to this node now. And then we do temp set left of parent. So we change this arrow, parent or pointer is going to get scooted up to like here, PTR, and it gets set to this. I know, very, very beautiful. But we go from this sort of thing to that sort of thing. No questions, Your Honor. For the rest of them, or for our right rotation, it is going to be the exact same thing, just mirrored. And now we can look at our left-right rotation and our right-left rotation. So let me get a little bit of clean workspace. I'm going to go steal the graph we are already doing this on. Perfect. Then we'll grab a different color because I do not like this lime green. Okay, for our left-right rotation, this was left-right. Yeah, perfect. We are going to take parents get left. So we know that right here, I'm drawing with the eraser. I'm losing my mind apparently. We know this portion needs rotated. So we're going to set 8 as our parent. So parent is equal to 8. We're going to set parents left equal to a left rotation on temp. So temp is equal to parents left it may want us to start at 12. So let's change it to 12. Let's see what this cooks. So parent is equal to 12. We're going to set temp equal to 8. So I'm going to put parent in blue and then temp in 8. And then we're going to do a left rotation on temp. So if we come back up to here, we have to do our left rotation. I'm going to change colors. So now we need a left rotate on 8. So we set this temp. So this is going to be our parent in this function. This is going to be our temp. Temp is equal to parents right. We do parent set right is equal to temps get left. So we move this arrow to point to 9. And then we do temp set left parent. So we turns 10s left, and we point it at 8. So it's going to look like 8, 10, 9, and 6. And then we return temp. So we return 10 from this function. So coming back to our left-right rotation, we are going to set left into what this function returns. So we are going to set 12's left to 10. I guess it would, I'll draw the big ugly line. It's going to point here. And then we return the right rotation of parent. So let me redraw this graph real quick. So we have a 12 and a 15. And now we need to return the right rotation at 12. So let me grab another different color. Yellow. Yeah, that's ugly. We'll use it. So let's go find our right rotation. First things first, we're going to set temp equal to parents left. So temp is equal to the 10 node. Parent set left is equal to temps get right. So nothing happens. We set left equal to null. And then we take temp and set its right as the parent. So we delete this. And we're essentially scooting all of this down here. So 12 and 15. We did it. So if you want to master your rotations, I would look through the code. If you want to memorize the code for it, you don't have to memorize the code, but you need to understand how these rotations work. And then to balance, if balance factor is greater than 1, we know we need to do a right rotation or a left rotation. A right rotation or a left right rotation. And the way we check that is we say at our root is the balance factor greater than 1. And then we say if the difference on our left portion is greater than 0, we do a right rotation. If it's not greater than 1, so if it's a -1 or -2, we need to do a left-right rotation. I don't expect you to memorize this portion. You know, you don't have to sit there with flashcards and be like, okay, if it's -2 in balancing factor, don't worry about it. But yeah, that is all of the... It's gonna whine at me, isn't it? Oh, you're not allowed to see my tests. Open balance trees, AVL programs. Go ahead and run it. So let's rebuild this tree. So we're going to insert a 12, insert 8, insert 15, insert 6, insert 10, insert 9. So we're going to do a check out the traversal for all of them. So for our in order traversal, it'll go as far left as we can, print, and then go as far right. So we get 6, 8, 9, 10. I had to think about that. That's my bad. 12, 15. So we know that our tree works. And then let's display the balanced tree. So our final product after hand jamming this was 10. 10 points to 8 and 12. 8 goes to 6 and 9. And 12 points to 15. So it works. Pat yourselves on the back. We have balanced a tree. So looking at the insert, because this is the difference between the two codes, we create a new tree node, set the value. We ask, should it be the root? If it's not the root, we have to find where it is, and we just do the binary search tree things to get there. So while we haven't hit a leaf node, if the left side is smaller, we go left. If the right side is smaller, we go right. At the end, we balance it, and we return the root. So looking at the recursive one, I don't know why, but I'm such a sucker for recursive functions. So we ask, should it go as the root of the node? So if node is equal to null, we have to set it as root. Else, If num is less than the left side, node get value. Yeah. If it's less than, we will insert left. So we call node set left, insert node get left num. Else, if it goes on the right, we recurse down the right side. So that's all the code for the chapter. It's not too bad. I turned touch back on, darn tootin'. And now we can cover red-black trees. So with our AVL trees, we use height to determine whether or not it's balanced. Balanced. For red-black trees, we actually denote colors for our nodes. Now, fair warning, red-black trees are the death of me. I hated them when I came into this class, however many years ago, and I'm still not a big fan of them. I feel like they overly complicate, but it is a different implementation. We don't. I don't have code to show you for this, so Google it, check iBooks. So red-black tree. Couple rules we have to put down. A red-black tree is a binary search tree. Every node is either red or black. The root has to be a black node. A red node's child cannot be red. So, if we want to write these rules out, so BST, we use two colors. We start on black. Red cannot have red child. And a null child is considered to be a black leaf node. So clear as mud, right? It's only going to get clearer. So one more set of rules is all paths from the node to any leaf descendant node must have the same number of black nodes. So if we look at this tree, or the one on the right, we have a black node to start, and our left node is red, and our right node is black. Now, two black nodes, so black, black, that's not in the rules, that's fine. The issue is looking at how many black nodes are in a path. So if we go 86 to 25 to the left null child, there's only two black nodes, the leaf and the root. If we look at the right side, we have a black 180 and a black leaf node. This has three black nodes in it, which fails the red-black tree test. Looking at the left one, our 180 node is now red, meaning that all of these have two black nodes in their path. If you want a larger black tree example that doesn't look like a rainbow threw up on it, this passes. So we have a black node to start, all of our leaf nodes are black, and any path that we go down follows the number of black rules. So with this path, we have three black nodes. We have 75, 30, and a leaf node. If instead we go here, we still have three. If we walk all the way down here, so 75 to 40 to 50 to 45, we also have 3, 3, 3, 3, 3. You get the idea. So, red-black trees are a pain in my ass. They have super strict rules, and you have to make sure that whenever you insert or delete, that all of these rules stay valid, compliant, whatever you want to say. And here are the rules for inserting. So, first things first, we have to create a new node. That rule's easy. We can do that already. We start as a red node. Got it. We insert node into the tree using BST rules. We've been doing that for months now. We can do that. Assign parent with nodes parent, uncle with nodes uncle, and grandparent with nodes grandparent. So we have a lot more data in this tree than we've had before. So a red black node, so RB node, we're going to have a left child. What do we even need child? I'm writing the child down. So left child, right child, parent, uncle, grandparent, and value. Because you have to know what you're balancing, right? So that's a lot of data to keep track of. And for uncle, what it would be, that's supposed to go that way, is, if we wanted to insert something right here, the parent would be this one, the grandparent would be the root node, and the uncle would be diagonal in a way. So if the node is the tree's root, so if we have nothing in our tree, we are going to color node black and return. We found a spot for it. If the parent is black, then return without any alterations. So if we have a black parent and we insert a red on either side, we're chilling. If parent and uncle are both red, so if we have a red, red, and a black, we want to insert like here, then color parent and uncle black, color grandpa red, and recursively balance grandparent, and then return. So we say you're no longer red, you were black, uncle is black, we make grandparent red. We have to do some sort of rotation here to fix it. If node is parent's right child, so if node is here, parent is here, and parent is grandparent's left child, then rotate left at parent. Update node and parent to point to parent and grandparent respectively and go to step 7. So we can look at this in a second. We have an example built in. If node is parent's left child and parent is grandparent's right child, so same song and dance, just mirrored. Parent would be on this side, node would go here. Rotate right at parent, update node to point to parent and grandparent respectively, and go to 7. For rule 7, we color parent black and grandparent red, and then we do another rotation. So let's build a tree. Let's get funky with it. So first things first, we're going to insert 86. Since there's nothing in our tree, we're going to color it black and return that. So all our tree has right now is 86, and it will be black. Can I choose it? Yes. I want to white, purple. Yeah, that looks good. So now we want to insert 180. So we're going to create a new node. So create a 180 node, make it red, and then find the spot it should go, which is right here. So let's go ahead and place it there. So we put 180. Okay, so we got it in the right spot. Now we need to insert 92. We're cooking here. So we create 92, make it red, and go to the spot where we want to put it. So it would go right here. Okay, we got that in. Now we need to rotate. So we are going to, this is rule, I want to say 6. Yeah, because we have an elbow basically in our graph tree. So we have to rotate right at parent, update node and parent to point to parent, and go to step 7. So we do a right rotate on 180. So we hit them with one of these. So we will have 86, 92, 180. It's supposed to be black, red, red. Now we have to go to step 7, where we fix the colors. So step 7 is color parent black and grandparent red. So since 92 is our new parent, this is going to be black, 86 will be red, and then finally we do a left rotate. So we will have 86, 180, and then a 92 as the root. If you really want to remove, you can look at that on your own time. I am losing brain cells as I explain red-black trees to begin with. What do you need to know for the exam from this chapter? So AVLs and red-black trees are ways to balance binary search trees. It makes them more efficient. Am I going to sit down and say, hey, you should write down the insertion code and the deletion code steps? No. No. Just be aware you have multiple steps that you have to take, and you may have to change node colors or do rotations in order to comply. You should know the rules of what makes a tree a red-black tree and be able to look at it and tell if it is a valid red-black tree or not. And then went ahead and gave you an example question that I'm going to tell on the final. Suppose the tree in diagram X is an AVL tree. Go ahead and balance it, and then draw the tree after it's balanced. So you are going to need to know your AVL balances. That's it. I'm going to go day drink after having to think about red-black trees. So, good luck. Take it easy, kiddos.